Hey, so this is Joe, and this is the second part of the 11th chapter of Stewart's Calculus, and we're going to be talking about infinite series. And so there's a lot to know about infinite series if you've looked in your book at all, and we're going to kind of I'm going to kind of break that up into two parts. So for this part, I'm going to be talking about what an infinite series even is. I'm going to be talking about a couple kinds of infinite series, and I'm going to give you two tests to test whether an infinite series converges or diverges, and I'm obviously going to kind of elucidate as to what a convergent or a divergent series is. So let's jump right into it. An infinite series, you can also just call it a series. It's kind of assumed that it's infinite if you're talking about it, because just a series on its own between two real numbers is very interesting. And that's the sum of all of the terms in an infinite sequence. So that means, like kind of out symbolically, if we were to have a sequence A of n, we'd write out an infinite series out of that sequence. And again, these series, like sequences, always start at 1. That's really just a convention. They can start at other values, but most of the time we use 1 so that what the sequence looks like, the sequence that we use, looks a little nicer. So between n equals 1 and n is infinity of a of n. And so this is an infinite series. This is the series where we add all of the terms in a of n, and we can write that out as a sub 1 plus a sub 2, the second term, plus the third term, plus the fourth term, plus, and then all the way out to the nth term, and then add some more. And so that is basically what an infinite series is. And the product, I don't want it, no pun intended, of an infinite series are things like numbers with infinite decimal places, like pi. You can express pi as an infinite series. You just add a bunch of little fractions together, and those fractions become littler and littler and littler, and you make that into some generalized pattern, and then that's an infinite series. And so the most important thing for Calc BC using infinite series, well, not the most important, but one of the most important things, is figuring out whether or not a series converges. And so we know that sequences can converge. So that should mean if this sequence gets to some definite number, there definitely should be series that converge, because if they get to a definite number, that means that there's probably some definite number of terms you can add, or some countable number of terms you can add, and that will give you an actual number. So we say that a series converges when that series, and so I'm just going to write out the summation sign, and from now on I'm just going to write out the summation sign, and I'm not going to put these limits on, and we're just going to assume that it's 1 to infinity if it's not anything else. On the AP you should put the limits though. So we say that this series converges if, when we add all the terms up in either some formulaic fashion or actually just by brute force. You'll never be able to do it by brute force though, but if you're able to add those up, that will equal some s, and that s is a real number. So basically, a convergent series is a series that adds up to something real, and then a divergent is if instead it equals either some non-computable form, some indeterminate form, or it equals plus or minus infinity. And so we have a bunch of tests in calculus to figure out whether a series converges or diverges. And I'm going to get to those tests a little bit later. For now, I'm going to give you a couple, or actually I will give you the first test. Sorry about that. The first and most basic test that's very similar to the limit test used to figure out whether a sequence converges or diverges is also the limit test, but this is the series version of the limit test. So initially, this limit test for series, a series style of it, really only is a reliable test for divergence of a series. So if we have a sequence that we're adding all the terms of, so we're making it a series, the sequence in that series, if we take the limit as n approaches infinity, and it's equal to 0, that limit is equal to 0, then we know that the series could converge, but it won't necessarily converge. This isn't enough proof to prove that that series will converge, that it'll add up to a definite number. However, we do know if that limit is anything but 0, so that if it's undefined, if it doesn't exist, if it's infinity, if it's some other number like 1 or 2, then we know for sure that the series of a of n is divergent. So, now I'm going to tell you about one of the most common kinds of divergent series. It's so common and so easy to use for comparison tests, which we're going to be talking about in the next video, that it has its own name. It's called the harmonic series. And it comes in the form of the series of 1 over n. And so we can write that out as 1 over 1, which is just 1, plus a half, plus a third, plus a fourth, plus 1 over n. That's the harmonic series. And so let's run this limit test to see if the harmonic series diverges or converges. So we'd have to take the limit of the series inside 1 over n. So the limit as n approaches infinity of 1 over n is 0. Well, it's inconclusive. We don't know if it's divergent. We don't know if it's convergent. I will tell you, though, the harmonic series always diverges. Always. And so this is a good series to remember later on when we start comparing series to figure out if one is divergent or convergent. The harmonic series, 1 over n, always diverges. And the limit test, it's good to figure out if something's divergent. It's a good one to do at first when you're given a series and you want to figure out whether it's divergent or convergent. The limit test is a great one to start off with. However, it can only do so much for you. So let's go on and talk about another kind of series. This kind of series is also a really important one for a couple of reasons. So it's called the geometric series, and it comes in the form of some constant a times a constant r to the n minus 1. And remember, it starts at 1 and goes to infinity. And the first reason it's important is it always converges if the absolute value of r is between 1. So in other words, if r is between 1 and negative 1, then this series always converges. And so when it comes to infinite series, it's difficult enough to figure out if a series converges or diverges, but very rarely do we actually have the opportunity to figure out what the sum of that series is, because that's a different thing, right? So we're going to have a bunch of tests later on in this chapter that kind of test convergence and divergence, but none of them indicate the sum of the series. We just know if there is going to be one. But the geometric series, we actually do have a nice little formula that will tell us the sum. And that formula is, and so that means that we can actually say the series equals something. This is a rare kind of big moment. We can say that this series equals a over 1 minus r, but this equals is conditional on it being convergent. And that kind of makes sense. A convergent series means that it adds up to something, and if it's not convergent and it doesn't add up to something, we can never say that it's equal to anything. But if it is convergent, a geometric series is equal to a over 1 minus r. And so all you need to do if you encounter a geometric series on the AP, on the free response, the only justification you'd need to say that it's convergent is just say it's a geometric series, and maybe like point out and say that the absolute value of r is less than 1. You could even plug into this little formula and show what it adds up to, and then you just need to say because it's a geometric series and then move on. That's it, but this is a very important kind of series for that. And then another important one is called a p-series. And a p-series comes in the form 1 over n to the p. And this is a special series because it always converges if And you can say, well, when p is 1, that just turns into a harmonic series, right? How can it converge? Well, we'll prove that later with some comparison tests, but in the next video. But it converges if p is greater than 1. So if we have 1 over n squared, 1 over n to the third, 1 over n to the fourth, that series converges. However, 1 over n always diverges. And so this p series, the geometric series, and the harmonic series are going to be very helpful in the next video. So bear them in mind, and also kind of keep your eyes peeled for them when you're doing some practice problems. Now I'm going to give you the second of the 2 tests that I promised in this case to prove divergence or convergence of a series. The limit test is a little weak, but this test, the integral test, is actually quite strong. And also, by the way, there are proofs for all of these convergences that I've been talking about with these series in your book. I'm not talking about them right now because they're important and they're interesting, but it's more important that you just know this stuff. But I do encourage you to go and look at the proofs as always. But so now the integral test. Let's go. Alright, so the integral test has a couple of conditions, but it says if we consider the sequence, so basically the general formula for a sequence, to be a function of n, and if that sequence is continuous, positive, and decreasing, and it needs to meet all 3 of these criteria, and on the free response section you have to basically write down checks for all 3 of these conditions before you're allowed to use the integral test. If all that's true, then the improper integral from 1 to infinity of f of x dx converges. Then the sequence, the series of a of n, the infinite series, also converges. So that's pretty nice. We've dealt a lot with converging integrals. And I'm not going to give you a proof for this right here, but I'm going to kind of give you the intuitive understanding. So say we've got some exponential decay function right here, one that we know goes to a definite area, 1 over x squared. We know that this is a definite area right here, right? But what if we have some sequence that we call 1 over n squared? 1 over n squared. So that sequence would only happen, remember the sequence isn't a smooth function like this, it's a bunch of points. So we're going to have 1, 2, 3, and so at 1, and this is n, let's call this n, and let's call this a of n, even though this is in terms of x. Remember, we're just kind of changing the variables for the integral and then for the series. So when n is 1, a of n is also going to be 1. When it's 2, it's going to be a 4th. When it's 3, it's going to be a 9th. And let's say we try to get the areas of all these. Well, we'd have to use Riemann sums, right? That's all we have because we just have a bunch of points. And so it would end up kind of looking like this. Well, we can say to ourselves, if the area under this curve that touches all the same points, I'll just write out an n. If the area under this curve that touches all the same points as the Riemann sum area for the series, if that smooth area reaches a definite value, wouldn't it make sense that the Riemann sum area would also reach a definite value? Yes, that's kind of the theory of the integral test. However, remember, the sequence has to be continuous, positive, and decreasing. You can't have a negative alternating series, it can't have a discontinuity, and it can't be increasing or both increasing and decreasing. So that is the integral test. And so now let's do some practice problems in which we're going to be using the integral test a little bit. So let's go. Alright, so we've got a series n over n squared plus 1. So the first test, and we were asked to figure out on number 7 whether this converges or diverges. So the first test we should do, if we don't have like any kind of inklings about it, is our limit test. Just see if it diverges. And if the limit's equal to 0, then it doesn't diverge, then let's continue on. So we're going to take the limit as n approaches infinity of n over n squared plus 1. We get infinity over infinity. We can use L'Hopital's rule. It's great, so that means that we've got the limit as n approaches infinity of 1 over 2n. We put the infinity in there, we get a 0, so that means it doesn't diverge. It could either convert, and it might converge, but it still might diverge as well. So let's go on to our integral test. However, before we do that, we need to prove that it is positive. Yes, it's positive. It starts at 1. It'll never be negative. That it's decreasing. Well, we put a 1 in here. We get 1/2. We put a 2 in here. We get 2/5. 2/5 is less than 1/2, so we can say it's decreasing. And it's continuous. Yep. And the only thing that would make this discontinuous is if this term we're ever able to equal to -1, and if not. So good, we can use our integral test. So what we do is we have our integral from 1 to infinity of x over x squared plus 1. Remember, we're just making this a function. And this is going to determine whether this converges. And so remember, this is an improper integral. It's actually a limit, so we do need to write this out as a limit as t approaches infinity between 1 and t of x over x squared plus 1 dx. You need to write that out because first off, you'll be able to use limit rules later, and also the AP wants just to know that you know that that's an improper form of an integral. So first what we're going to do, let's make a little u substitution. U is going to be equal to x squared plus 1. du is going to be equal to 2x. We see the x there, we don't see the 2, but we'll be able to take care of that in the coefficient. So we're going to have a 1/2, 1 to t. We see the x and the dx. We see the x and the dx, we can get a du. And then we've got a u in the bottom. That's going to end up being a natural log. Oh, wait, sorry. U, the 1 right there, we plug the 1 in, that's going to make the u2. This t will be something different. It'll be something times the infinity, but the t is just an infinity, so I'm going to keep the t there. It's fine. T approaches infinity of 1/2. du over u, when we integrate that, that's going to be the natural log of u, but I'm just going to plug back in for the u directly. That's going to be the absolute value. Remember the absolute value of x squared plus 1, and that's going to be between 1 and t now that we're back in terms of x. And so when we evaluate this limit and we put in a t into the x squared and we put in an infinity for that t, actually we need to, let's just plug in directly. Okay, we're going to go in directly and plug in the t. So we're going to get the limit as t approaches infinity of 1/2 the natural log of t squared plus 1 minus the natural log of 2. And all that times 1/2. Now, when we plug the infinity in here, we will get a natural log of infinity minus some definite natural log. But remember, based on our properties of natural log, we can make this a quotient in the argument. So we'll write out as t approaches infinity of 1/2 the natural log of t squared plus 1 over 2. But when we put that infinity in there, this expression will still end up being infinity. So that means that the series is divergent by the integral test. You need to put in by the integral test. Just to give a reason for this, for such a conclusion, and say that you know what test you're doing. So that is kind of a simpler problem version of the integral test. We're going to come over and we're going to do one more, one that's a little bit more difficult. Alright, so we're going to do number 19, and it asks us to figure out whether this series converges or diverges. So first we're going to do our limit test to figure out if it diverges. And so we've got the limit as n approaches infinity of the natural log of n over n cubed. We're going to use L'Hopital's rule because we put an infinity and an infinity there. We'll get infinity over infinity. So by L'Hopital's rule, we've got as n approaches infinity, this turns into a 1 over n, and this turns into a 3n squared, but because there's another n, that's going to be a 3n cubed. And now when we put the infinity in here, this is going to be equal to 0, so we don't know if it diverges or converges. It could be either. So we're going to go over and do our integral test. And we need to prove that this is positive. Yes, it'll never be negative. it's decreasing. Yes, the denominator goes up a lot faster than the numerator. N cubed goes up a lot faster than the natural log of n. So all the preceding terms are going to be get smaller and smaller. And it's continuous. Yes. So we can use the integral test. So we're going to get the integral from 1 to infinity of the natural log of x over x cubed dx, and we're going to write this out as a limit. The limit as t approaches infinity between 1 and t of the natural log of x times x cubed dx. And now it's looking like we are going to need to use our integration by parts technique. So we're going to get a u. The u is going to be the natural log of x because we don't know how to integrate that, so we're going to differentiate it. Our dv is going to be x to the negative third dx, so that means our du is going to become dx over x, and our v is going to become a negative 1/2 x to the negative half. So we start plugging this all in. We're going to get the limit as t approaches infinity of, so our u times our v, that's going to get a negative ln of x over 2x squared between 1 and t, and minus, but since we have a negative v and minus is a plus, the integral between 1 and t, and that's our v du, 1/2 x to the negative third dx. And so now this we can integrate, and this we can evaluate, and we've got our limit out here, so we are all set. This out here is going to become, well, actually we need to separate this out into two limits first. So actually, yeah, let's separate this out into two limits on the next screen, and then we will start evaluating, because it's a lot easier that way, because we'll be able to use L'Hopital's rule over here because we need to. Alright, so we've separated this out into two limits. Now we are going to get well, let's apply L'Hopital's rule right here. So we will get the limit as t approaches infinity, because remember, you put an infinity and infinity in there, it'll turn into a negative infinity over a negative infinity, or negative infinity over positive infinity. So that will give us a negative 1 over 4x squared when we take the derivative of both the numerator and the denominator, and that's still between 1 and t, plus, and then we've still got the limit as t approaches infinity. We integrate this, that will become a negative 1/4 x to the negative 2, and that is going to be evaluated between 1 and t. And then here we can actually start plugging in for t. When we put t in and that becomes an infinity, that'll be a 0. Minus and a minus is a plus. We put the 1 in there, that's going to be a quarter. And then minus, you put the t in there, the x is going to be in the denominator, the t is infinity, that's going to be a 0 as well. And you put the 1 in there, that will be a fourth. So we've really just got a fourth and a fourth, and that is going to be equal to a half. And so since the integral is equal to an actual number, we say that it is convergent, the series, by integral test. And there you have it. That is it for part 1 of Infinite Series. Stay tuned for the next part and for the rest of this chapter. It's really great. Thanks for watching.